All right, this is the video for chapter one. The video for chapter one is going to be very brief. I'm not going to go as much into the detail as for chapter one as I will for the remainder of the chapters, just because for the first week of class, I will pretty much go over chapter one in class, but you'll kind of have this as a supplemental instruction for if we are behind in class and we can't finish something, I will tell you to come on the videos and watch them. You should probably watch this video though during the first week of class after the first day that we meet, so that when we do have class, we can kind of go through this a little bit quicker than usual, just because this should be all review for you guys. But I do understand that people forget a lot of the information that they've learned from their Gen Chem. So we will get you caught back up on your Gen Chem. So chapter one basically is about structure and bonding and about acids and bases. But first, let's just talk about what this class is about. All right, why are you taking this class? So what is organic chemistry? All right, really the basis of organic chemistry is anything that contains a carbon atom. Now it's not perfectly true because, for example, carbon dioxide, CO2, is not considered an organic molecule. So there is kind of more to it. It's really anything that has a carbon, a hydrogen, and is not a salt, like an inorganic salt. So that is not really considered an organic molecule, but pretty much if it has a carbon and hydrogen on it, most likely it will be considered an organic molecule. Every living thing is made up of organic molecules, but there's also non-living things that are also composed of organic molecules. We'll talk about those. Proteins are made up of organic molecules. I got these slides from your publisher, so it's not just proteins in hair. Okay, you have your whole body is proteins. Your skin is protein. Your organs are made up of protein. Your proteins hanging out of your cells. Everything is protein. The DNA is an organic molecule. Foods and medicines. Here are just some examples. I mean, in your everyday life, you deal with organic molecules. From the second you wake up to the second you go to sleep, you are dealing with organic molecules. These are just kind of examples, like Lipitor, a cholesterol drug. A lot of people have heard of it. You can kind of see it's a very complicated structure. This is what's called a synthesized drug. We're going to talk about in the next few slides. There are really two types of organic molecules that we deal with. One are things that are found in our environment, our natural environment, called a natural product, like cholesterol is a natural product. This is found naturally. Our environment makes this, but Lipitor and Vioxx and OxyContin are synthetic drugs. They're made in a lab. OxyContin is kind of what we would call like a semi-synthetic drug. I'll talk about that in a little bit. And penicillin, here's an example of penicillin. But these are just kind of interesting molecules just to kind of look at. And right now it might look completely weird to you, but by the end of the semester, you'll be looking at this and seeing things that you haven't seen before. You're definitely going to look at the world a different way after this class. Okay, so the origins of organic chemistry. So like I said, it's the chemistry of carbon. That's not exact. There's a little bit more to it, but 98% of the time, if you have a molecule that has a carbon, it's going to be considered an organic molecule. Okay, compounds are contained from plants and animals and other sources. There are really two types of molecules that we deal with. One are natural products. These are naturally occurring. These we find in our environment, like sugar is a perfect example, morphine, aspirin. I mean, you can think of thousands of molecules. Right now, you probably can't think of them, but in class, maybe we'll go over some more, or if you guys have other examples, we can talk about them. Then there are synthesized, and then what's also called partially synthesized. I guess that's a third class, but I kind of put it under synthesized. So a synthesized molecule is something that is absolutely not even found in our natural environment, like plastic. Plastic is not found in our natural environment. Okay, so that's completely synthesized. A few of those drugs, like Vioxx and Lipitor, those drugs are not found in our natural environment. They're completely synthesized. But a partially synthesized molecule, perfect example, is heroin. if you take morphine, okay, which comes from our natural environment, and you change it a little bit, and we will talk about this chemistry in class, if you change it a little bit, you will get heroin. So heroin is kind of a form of morphine. Okay, so that's a perfect example of it's partially synthesized. It's isolated, like the morphine is isolated out of our natural environment, then it's taken into the lab and it's then changed a little bit in laboratory. Our environment, our natural environment won't do that, but we take something from our natural environment and change it. Okay, there's also a few sugar substitutes that actually come from sugar, that you actually take sugar, you change it a little bit, and you now have a 0-calorie sweetener. So that's also another example of a partially synthesized molecule. Okay, so where did this branch of chemistry come from? About 150 years ago is kind of where it really all started. Initially, people thought that organic compounds came from only living sources. Okay, they call it a vital force, meaning if it came from a living source, it was considered organic. If it did not come from a living source, then it's called inorganic. And that's what the definition was. Okay. However, Waller was a scientist in the 1800s. We'll talk more about him in class. He basically proved that this is not correct with an experiment that he took urea, which is the main component in urine, which obviously is an organic molecule because it comes from a living source, and he converted it into an inorganic molecule. So he took something that was organic and converted it into inorganic. So that kind of changed the whole view of this, because people thought, hey, if it's a living source, it will always be a molecule that comes from a living source, and the chemicals that he converted it to do not come from a living source. So that kind of changed our definition of organic, and pretty much it's really anything that has a carbon atom in it. Okay, so this class. So I, as a joke, I always tell my class, everyone's always afraid of organic. It's so hard, but this class is really only about one molecule. It's about carbon. Your Gen Chem is about all the atoms. This is only about carbon, so how hard could it really be, right? Obviously, that's a joke. There's lots of things that carbon can do. Okay, so we've already talked about organic is the study of carbon. So why is it so special? So here's carbon on the periodic table. Okay, we'll talk a lot about it, but kind of a few things is that 90% of compounds on our planet are considered organic. 90%. So only 10% of the molecules on our planet are inorganic. Okay, so we're talking millions and millions of chemicals and compounds that are organic. So it's a pretty important branch of chemistry. Okay, it is in the 4A group. Okay, it has 4 valence electrons. If you guys remember from your Gen Chem days, remember the group 1A all have 1 valence electron. Group 2As have 2 valence electrons. Group 3A, 3 valence, 4 valence, 5, 6, 7, 8 valence electrons. Okay, so if you guys remember the Lewis structures, you always do this. And again, we're going to talk more about this, and just to kind of remind you about this, again, I'm trying to bring back all those memories. There's 4 valence electrons, octet rule, things want to have 8 electrons, so carbon is going to gain 4 more electrons. Electron here to pair up, electrons want to be pairs, so notice this is 4 different bonds. Carbon makes 4 bonds, and they could be combinations of singles, doubles, and triples. Okay, so because of it, it can attach to other carbons, it can attach to nitrogen, to oxygen, to any of the halogens. These are called the halogens: fluorine, chlorine, bromine, iodine. All right, phosphorus, sulfur, hydrogen. This slide is kind of highlighting the common atoms that we're going to see over and over again throughout this semester. Okay, obviously it's not just carbon. Carbon has to attach to other things to be a molecule. So it's mostly attaches to hydrogen, and then you get oxygen, nitrogen, phosphorus, sulfur, and then the halogens. All right, we will talk a little bit about magnesium, all right, and sodium. These two will be kind of talked about, but very small amounts. Okay. Also, depending on who your Gen Chem teacher was, we usually talk about that if you have an atom from the 1A group, they always have a +1 charge. Because lithium, remember, atoms want to have the same number of electrons as their closest noble gas. Whichever noble gas is closest to it, that's the number of electron or the electron configuration that it wants to have. So lithium is in between helium, okay, and neon. So is lithium closer to helium or closer to neon? It's not a trick question. It is closer to helium. Well, how many electrons does it have to lose to have the same number as helium? Okay, it needs to lose one electron. That's going to have the same electron configuration as helium. Okay, so therefore lithium gets a +1 charge. Okay, so everything in the two-way, with the exception of hydrogen, do that. They all have +1s. Okay, beryllium, magnesium, calcium, strontium, barium. The closest noble gas is the one prior to it. So the closest one for magnesium would be neon. So it's going to lose 2 electrons to be like neon. Aluminum, same thing. All right, what's closer? To lose 3, so if you take aluminum, to lose 3 to be like neon, or gain 5. Okay, obviously losing 3 is better than gaining 5. So aluminum, gallium, boron, indium, thallium all want to have a +3. Okay. Now let's say you go to the halogens. Okay, fluorine, neon is closer. So fluorine's going to want to gain an electron to be like neon. Oxygen's going to want to gain 2 electrons to be like neon. Nitrogen, gain 3 or lose 5. Obviously gain 3. Now we get to the 4As. Gain 4 or lose 4. What's better? Well, it's basically the same. All right, so most of the time in your Gen Chem days, we kind of ignore group 4A, especially the nonmetals. The metals we usually talk about, but the nonmetals, and remember, the periodic table, there's this line right here that kind of shows you where all the metals and nonmetals are. Things to the right are the nonmetals, things to the left are the metals, with the exception of hydrogen. Okay, so 4 is a special case, and I always tell my class, you'll learn about it in organic. We're not going to worry about it here, because you can basically have both a positive charge and a negative charge. Okay, so that's kind of why carbon is a little bit more important. It's in that no man's land where you can have both. Either lose 4, gain 4. It forms 4, has 4 valence electrons, so it forms 4 bonds, and it can pretty much bond to anything, non-metals and metals included. Okay, so this chapter, what's so important about this chapter? Basically, that is the key word for this chapter. All right, see how crazy I went with the writing? That's how important it is. All right, it's review. This is review. Most of the stuff you will have seen from your last classes. If you took Chem 101, there's some stuff in here that you've never seen before. If you took Chem 111 and 112, you definitely have seen everything. There's something about hybridization in here that most people haven't seen, or if they even have seen it, they might not understand it. So we're going to emphasize a little bit more on that. But the things that I know everyone has had, I'm going to go over very quickly. But we will talk more about it in class if you guys need more of a clarification of it. Okay. I also have a handout. So, like I said, we're going to talk about atoms and bonds, geometries and acids and bases. I also have a handout that I will talk about in class. And this handout pretty much has a summary of a lot of the Gen Chem principles that are very important that you need to remember from your Gen Chem days. Okay, so let's get started. All right, atomic structure. Very simple. I'm going to start very simple on this, and then we'll kind of go from there. Structure of the atom. This you should know. I mean, you learn this like in 3rd grade, maybe even 2nd grade, maybe even 1st grade. All right. But you basically have a nucleus. All right, here's your nucleus. Okay, it's composed of protons and neutrons. All right, it has a positively charged nucleus. It's incredibly small, and this is where the majority of the mass is. So the mass is in your nucleus. Okay, and then around it, the sphere, how they kind of show this blue sphere here. All right, this blue kind of area. All right, that is where the electrons are found, and it's kind of found in that volume of space. They're negatively charged. It's actually called an electron cloud. Okay, and it's the majority of your volume. That's where your volume is. Okay, I'll kind of like to give a visual of how incredibly small not only are atoms, but also the size of the nucleus with respect to how much volume there is, because people don't quite understand. They don't realize your nucleus is a tiny, tiny, tiny dot inside of this gigantic sphere of electrons. Okay, so I saw this kind of a visualization. So imagine, I have to look at my notes just to kind of remind myself of it. So imagine you have an atom That's the size of a football field. Okay, so imagine an atom, one atom. We're talking about one atom, the size of a football field. Okay, that's a pretty darn big atom. All right, the nucleus will be in the center, and the size of that nucleus will be the size of a marble. Okay, just to kind of give you an idea of the size of your the volume that the electron occupies and the volume of the nucleus. So imagine you have a marble. So imagine you have a football field. Right, here's a football field, 100 yards. Okay, all right. So that's your atom, and inside of it, and imagine a marble at the 50-yard line. That's your nucleus. That's the size of it. All of your mass is inside of that marble. Okay, just to kind of give you an idea of how dense. You see here, very dense. All right, all of that mass of your nucleus is packed into that thing so incredibly tightly. All right, very strong forces are inside. That's why atomic bombs have so much energy, because what you're basically doing is you are splitting the nucleus. So all of that, there's so much energy that's stored inside of that nucleus because of the fact most of your mass is in there and it's so dense. Okay, as soon as you hit it and the thing breaks, all of that energy is released outside of that nucleus. Okay, so that's kind of a crazy visualization to think about. That if you have an atom the size of a football field, or I mean, imagine an atom, like the size of where the Broncos play. All right, of Invesco Field. All right, so imagine you've got this atom that big, and the marble is the nucleus. I mean, that is so tiny. All right, so I think it's a great visualization just to kind of understand. And then also think about how incredibly tiny atoms are. All right.